Okay, so I'm going to swap over to the old mic here. So I carefully prepared some slides to answer the specific question that just came up. We're trying to be very proactive here. I'm going to talk about some of these more advanced techniques that we can use on our full portfolio of instruments for BioPharma characterization. I want this to sort of be science, so this is the only sort of pictures of instruments I want to put up, but I just wanted to show that this QE, or Q-Exactive BioPharma, is in fact two instruments. It's an option that can be applied to the Q-Exactive Plus or the Q-Exactive HF. And as Aaron indicated, what this option does is it essentially brings us this high mass range mode. It adds that to the standard features, and it also adds what we call protein mode, which is designed for proteins between, say, 15 and 50 kilodaltons, where we lower the gas pressure in the HCD cell, and we increase the sensitivity for proteins of those kinds of molecular weight, where we want to acquire a long transient to get high resolution. And the HF uses the D20 Orbitrap. That's the smaller Orbitrap, runs a higher field and gives you more resolution for the same time of acquiring the transient. So these instruments, as Aaron indicated, are an amazing all-round instrument to do the peptide mapping, top, middle, down, subunit analysis, and intact. But we also have the fusion and the fusion lumos. And if you really want to do top-down, then these are the instruments for it. They both have the D20 Orbitrap, they run at very high resolution, and they have multiple fragmentation modes that you can use to get a better coverage with top-down. And then we also, as Aaron indicated, we still have the Exactive Plus EMR. And if you want to do only native work, this instrument is better than the Q-Exactive BioPharma for very high molecular weight complexes and for doing ligand binding type studies. But QE Plus, QE HF are our all-round instruments for BioPharma characterization. So with that said, let's look at some data. So this is the typical workflow for a middle-down experiment. It becomes rather difficult to do top-down on 150 kilodalton protein. So we prefer to do a reduction and look at light and heavy chain, or in this case, this is really the perfect way to do it, do an digestion followed by reduction. Now you're getting pieces in the 25 kilodalton range. And with instrument like the QE BioPharma, and especially with the fusion and the fusion lumos, you can do really extensive top-down sequencing. So, this is, I think, what was being alluded to. We only have one fragmentation mechanism on the Q-Exactive BioPharma with an HCD. It's the best all-round fragmentation mechanism, but when you go to the Tribrid series of instruments, then we can not only do HCD, but we can do CID, ETD. We can combine ETD with HCD in a particular scan mode called ETHCD. Albert Heck was talking about this yesterday in the session in the morning. And this isn't commercially available currently, but we have presented data using UV photo dissociation. So on the Tribrid system, you can do all of these fragmentation mechanisms, and it's really powerful for getting the most extensive top-down sequencing. So, why do you need high-resolution instrumentation to do top-down? I'm sure most of the people in the room are already familiar with this, but when you are fragmenting multiple charge states that are highly charged, you get a very complicated spectra. And at first inspection, it actually looks like it's noise or would be uninterpretable. But when you start to zoom in, you realize this is all data, and at high-resolution settings, 140,000 or 240,000 resolution settings, you can isotopically resolve all of these charge states and get really nice data. So this is really this high resolution accurate mass that the Orbitrap gives that makes the top-down experiment so good. Aaron's timer's just gone off. You're done, buddy.
Oh, great.
So this is what the sequence coverage looks like on the Q-Exactive Plus, Q-Exactive Plus BioPharma. doing HCD fragmentation, we can run this at 140,000 resolution. We're also running this with at lower gas pressures here, so that we're getting high resolution and we're getting good sensitivity. And then we used the extract deconvolution algorithm to get to singly charged representation of the spectra, and then we're using Neil Kelleher's software for the actual top-down assignments. And so, here's your first set of numbers. Doing this with HCD only, on trastuzumab, where we did the eyes digestion and then eyes digestion and then reduction, we're getting 49% coverage on the light chain, 38% on the FD prime, and 39% on the FC. So this is actually, for a single fragmentation mechanism approach to middle down, is actually very impressive. And so you can do real assignments and real work with an instrument like this to note modifications that have taken place either in production or even in vivo. So that's what it looks like on the Q-Exactive Plus. But we can do a lot more if we go to the Fusion or the Fusion Lumos. So this is just showing you how you can vary different parameters to get different results on the Lumos. So we're looking at trastuzumab again. You can do this with different target values. One of the biggest differences between the Fusion and the Lumos is the way we trap the ions to do ETD. And we have a larger trapping capacity now on the Lumos. And so you can go to higher target values, and then you get better ion statistics, and you get better sequence coverage. But you can also change the reaction time. ETD is a chemical reaction. If you do it over different lengths of time, you get different products. So you can spread out the fragments you get by choosing different reaction times. So in this way, you can modify your process and extend sequence coverage rather than just running under a single set of conditions. And this is just showing you here how when you acquire at different reaction times, the actual, basically plotting out what the masses are of the ions that you can assign. And obviously when you start to go to longer reaction times, you tend to get smaller pieces, and shorter reaction times, you get bigger pieces, but you can get more coverage by using multiple reaction times. So, here are the numbers, essentially. Now, we've used ETD, which wasn't available on the Q-Exactive BioPharma. We've also done ETD HCD, and as I said before, that's where we activate the ions in the ion trap with ETD, and then when we're taking them back through the ion routing monopole into the C-trap to inject into the orbitrap for mass analysis, we can give them further activation with the HCD cell ion routing monopole, as we call it, on the Lumos. And so, in some ways it's a combination of HCD fragmentation and ETD fragmentation, but in other ways you can actually get unique fragments that aren't present with either fragmentation mechanism, because you're essentially activating ions that have already been activated from one mechanism with a secondary mechanism. So this is just using, as I say, ETD and ETD HCD. Now we're getting up to 72% on the light chain and 60 or 67% on the FD and FC region. So we're doing better now than we would just with the Q-Exactive. And this is showing you how the extent of coverage you get using ETD with different reaction times, shown here. And then we did UVPD on an experimental system, and we put in different amounts of UV radiation energy in these two experiments. And we also did CID, so that's available in the dual pressure linear ion trap for fusion. So we've got multiple mechanisms here. And what you see is that none of them on their own, get you more than 50%, but you can combine all of these different conditions and then really get good coverage. So this is showing what happens when you add CID to ETD. So we're up at around 70% coverage now for these subunits. And if we add in UVPD, then we're starting to get into the greater than 70 up to 80% sequence coverage for these subunits. So I can actually show you where the coverage comes from here. So on the light chain now we're up to 80%, the FC we're up to 76%, and the FD we're up to 73%. So this is where we combine CID, ETD, and UVPD. So that's kind of state of the art for where you can get with antibody subunit top-down sequencing. So we're really starting to get to the point that you can do complete sequence coverage with the middle down. So, where else can you use ETD? So this is a trastuzumab again. This is the same slide that Aaron showed, I think. But basically, we can do this on the Q-exacted BioPharma. We can do this on the Fusion. And we get very high sequence coverage of the light and heavy chain. And for normal peptides, HCD fragmentation is very good. You get almost complete sequence coverage of the peptide, a normal peptide that hasn't been modified when you're using HCD. But when you get into ADCs, things start to get different. Now you're adding a linker and a warhead onto a peptide, and that linker and the warhead was designed to be enzymatically degraded once it had been intercalated into a cancer cell. And so a lot of the chemistry that's been put into the linker and the warhead to make it cleave off also make it susceptible to cleavage under mass spectrometry conditions. And so the problem that happens is when you're trying to really narrow down the site of modification of one of these ADCs is that when you do HCD fragmentation, instead of the peptide backbone breaking, what happens is the linker or the warhead or both of them just fall off, and now you've lost your site information. So because ETD really specifically cleaves the peptide backbone, you can use ETD to get much more information. So I'm going to show a little bit about that here. So this is the same sample that Aaron showed, where we could expect that lysines will be modified with linker and warhead or just linker, and then of course there'll be the different glycoforms, and then other kinds of post-translational modifications that BioPharma finder picks up. So, as indicated, there are multiple lysine sites that could be modified. A number of them get the linker and the warhead, and some that just get the linker. But some of these tryptic peptides you get have got multiple lysines on, and it's not easy with HCD to know exactly which lysine has been modified. And biopharma companies really do want to know the exact sites of modification because the efficacy of these drugs is not uniform just across. One DAR ratio is not the same as another DAR ratio in terms of efficacy. It really does matter which sites you've modified because they come off at different rates inside the cancer cell. And also the half-lives of these entities in the human body are different too. So if you don't have the right sites, as well as having the right DAR ratio, you're not going to get the same safety and efficacy as you expected. So in this case, BioPharma Finder has identified two tryptic peptides that have 3 lysines in them, and they've both been modified with a linker and a warhead. The question is now, with HCD spectra alone, can you tell the difference between these two? So just looking here at the first peak, this is an HCD spectra, and this is not as good an HCD spectrum as you would get for the unmodified tryptic peptide. And the problem is that linker and warhead is falling off, and you're not getting good sequence coverage of the backbone that still contains the linker and the warhead. So you can't assign specifically which one of these lysines has been modified. But if you now go and do this with ETD, we can get a complete sequence coverage here. I'm so excited about this slide for 2 reasons. One, because you've got this really good sequence coverage. And the other is, I'm from England originally, and I can say C and Z. So happy to be in Canada. So we've got our C and Z sequence, full ladder here. And you can see that we've got the Z3 and the Z4 ions. If I zoom in here, you can see where they come from. Here's our Z3, so we've got the 3 amino acids from the end, and here's our Z4. And when you do the math here, the mass difference between these is exactly the 3 amino acids. Sorry, let me go back here. I'm not doing well with this. So the mass difference here is exactly the lysine with the linker and the warhead on it. So just from these 2 ions alone, and you can see how clean they are in the spectra, you can completely, with complete confidence, know that the linker and the warhead have gone onto this lysine. And then for further confirmation, we can now look at some of the C ions, and if we compare the C17 and C14 blowing up here again, when you first look at the spectra, it seems complex, but you can come in here, both very clean spectra. There's a slight interference here, but it's nicely isotopically resolved. And then you see the delta mass here is just from the 3 amino acids in here. There's no linker and warhead. So we can very confidently assign this lysine site here as where the linker and warhead have been added, and you really can't do that without ETD fragmentation. So in summary, middle down with these antibody subunits, we can get between 70 and 80% sequence coverage now using multiple fragmentation mechanisms. And peptide mapping, of course, we can get 100% sequence coverage. But what I think is more important is by employing ETD fragmentation, we can narrow down exact sites of modification where we put on these very labile linker and warheads that are not really suitable to HCP fragmentation. And then finally, I'd like to thank my colleagues in San Jose and in Bremen for the work behind this, and be happy to answer any questions.